This video is on the objective compute the value of the test statistic using the expected frequencies for a chi-square homogeneity test. What we're going to see is that the procedure for calculating the chi-square test statistic in a homogeneity test is exactly the same procedure for calculating the test statistic for a test for independence. So I'm only going to do the one video on this, as if you go back and look at those videos from the chi-squared test for independence, the calculation of the test statistic is done in the same exact way. Alright, so again, if you want to see more about it, click on More Instruction. Look at their videos, their notes, their examples. Hopefully those help you. And in fact, I have a little bit of it here. So computing the test statistic for the chi-squared homogeneity test. So they have a little recap as to when do you perform this homogeneity test. So if you recall, the goodness of fit test can be used to decide whether a population fits a given distribution, a known distribution. But it will not suffice to decide whether two populations follow the same unknown distribution. So this different test, called the homogeneity test, can be used to draw a conclusion about whether two populations have the same distribution or not. So to calculate the test statistic for a test for homogeneity, follow the same procedure as with the test for independence. So again, you saw this before. So it's the same sum down here, right? You have these observed counts in each cell of a contingency table, minus the expected frequencies. Those differences get squared, and then divide by the that corresponding expected frequency, and you're going to add these values up for every cell of the contingency table, just like in a test for independence. Right, and the test for homogeneity is always right-tailed and blah, blah, blah. These expected frequencies, right, to find the expected frequency of a certain cell, you're going to take the total of that row multiplied by the total of that column divided by the total number of in the sample, right, the total sample size, which again, you've seen this before. And you can read through their example here. I'll let you read through this stuff on your own. Let's just get to the problem at hand, the question. So here, a survey asks a group of college students about their majors. It also groups the students by whether they are athletes or not. These values are recorded in the contingency table below. Which of the following tables correctly shows the expected values for the chi-square homogeneity test? Right. And again, the observed values are above the expected values in all these options here, right? The expected values are in bold. Alright, so for the homogeneity test, what we'd be testing is, is the distribution of majors for all athletes the same as the distribution of majors for all non-athletes? That's what we'd be testing in a homogeneity test. Alright, so I'm going to write this table down and get into how we calculate the test statistic for this chi-squared test. Alright, so here's the table that was given to us. Now, I don't have the totals in yet because, again, the totals are not part of the heart of the table, right? The actual data, the observed values. So for the students that were surveyed, 11 of them were arts majors and athletes, right? 6 were humanities majors and athletes. 22 were science majors and athletes. 19 of them were arts majors and non-athletes. 13 were humanities majors and non-athletes. And 9 of them were science majors and non-athletes. Alright, so then we put in the totals, right? And I'm going to put these in different colors because, again, they don't really belong to the table exactly. They're not the actual observed counts here. Down this row, this bottom row here, I'm going to put the totals of these columns, right? So we'll have the column totals. So the total number of students that were surveyed that were majoring in the arts was 30, right? 11 plus 19. The total, majoring in humanities was 19, and the total majoring in sciences was 31. Right. Then down this column here, at this last column, different color again, are the row totals. Right, the totals of each row. So how many of the students were athletes? Right, there's 33 and 6, that's 39. And then how many of these students surveyed were non-athletes? Well, that's 32 and 9, that's 41. All right, and then in the lower right corner, you have the total sample size, right? The total number of students that were surveyed here. So in this lower right corner, this is a totally separate number. If you add the row totals, you get 80. If you add the column totals, you get 80. Right? So there were 80 students in this survey, and this is usually given the lowercase n. Right, this was our sample size. All right. So again, this test for homogeneity, we'd be testing whether or not the distribution of majors for athletes, all athletes, right, the population of athletes, whether or not that distribution was the same as the distribution of majors for the non-athletes. Right. And we'd have to calculate this test statistic. Now, let's get into the expected counts first. Right, the expected frequencies for each of these 6 cells, right? There are 2 rows, 3 columns, total of 6 cells. And I know in all my videos for these, there's only been 2 rows and 3 columns each time. Just know that that's not always going to happen, in most textbooks, most exercises. Now for this particular, the Newton Alta stuff, I noticed they're doing mostly 2 by 3, 2 rows, 3 columns. Because that way there's, relatively few terms of the sum you need to find for the test statistic. Right, because this way I only need to add up 6 values for the test statistic. If it were a 2 by 4, then I'd have 8 values. If it was a 3 by 4 or a 3 by 3, I'd have 12 values or 9 values, right? So I think they're doing the 2 by 3s here, so that way you have fewer values to add up. They're trying to make it as easy as possible. All right, so let's talk about the expected frequencies. Now remember, the expected frequency for, say, the first row, first column. So I'm talking about the expected number of arts majors who are also athletes. If I have a sample of size 80, well, again, the way to calculate these expected frequencies is I take my row total, 39, multiply by the column total, 30, right, for that column, and divide this product by the sample size divided by 80. Right. And I'm looking at the options here. It looks like they're rounding all of these expected values to 1 decimal place, to the nearest tenth. Right. So I've got 39 times 30 divided by 80. All right. So, and I'm going to put this in the same table but in a light green color. And I'll put it underneath the observed values, right? So all the values in black are the observed counts, the observed frequencies, the O's, and then all the E's, the expected frequencies, I'll put in like a light green underneath. So this is approximately 14.6. Right? So that's for this first row, first column. Right? All right, and then the same for what's the expected count for the first row, second column, right? 1, 2 here. So now I'm here where the humanities majors that are athletes. So again, that row total is 39, that column total is 19. So it'd be 39 times 19 divided by the sample size divided by 80. And we'll round this to 1 decimal place. All right, so on my calculator, I'm just going to go change the 30, do second entry, re-enter that thing, just change the 30 to a 19. And it's about 9.3 if I round to 1 decimal place. So approximately 9.3. And after I'm done with all these, I'll show you a faster way to do it with your calculator. Now I'll just keep going. I'll just say ... here, and just do them. For this first row, third column, I'd be 39 times 31 divided by 80. Right? So I'm just changing now the 19 to a 31. So that's about 15.1, the expected number of science majors who are athletes, out of a group of 80, based on this observation table. Then the non-athletes who are art majors. For this, this row total is 41, this column total is 30, so 41 times 30, then divided by 80 again. All right, about 15.4, right, if I go to 1 decimal place. And then I just need to change the 30 to a 19 for the next one, right? So change the 30 to a 19, so about 9.7 for that expected value. And then change the 19 to a 31 for that second row, third column entry. And about 15.9. Okay, so there's all the expected frequencies for each of the 6 cells. Alright, so going here, that looks like it matches this one. 15.1, 15.9, 9.3, 9.7, 14.6, 15.4. The second option. Now, I guess you could have just checked the first row, first column, because the only one that has 14.6 as the expected frequency for the arts majors who are athletes is the second one. So you could have just done the first one. Right? But you're going to have to do them all anyway when you calculate the test statistic, which is the second part of the question. Alright, so again, they go through that and show you blah, blah, blah. Alright. Now, as I said, I'm going to show you a faster way to do that on the calculator if you haven't seen it already in other videos of mine. Another way to do this is to enter these observed counts in black, the 11, 6, 22 in the first row, 19, 13, and 9 in the second row. Enter these observed counts into a matrix. So I go second, hit this x to the -1 button. There's the matrix menu. See it says matrix there. Go over to edit, and I'll just do matrix A, number 1. And this matrix has 2 rows, 3 columns. So that's what these numbers are. Number of rows, 2. Enter. Number of columns, 3. Enter. And then I'll enter these observed counts. So we have 11, 6, 22, 19, 13, and 9. And I get out of here, quit. And then to get the matrix with all the expected counts, if you want another 2-row, 3-column matrix with these expected counts, you're going to just run the chi-square test. So I hit the stat button, go over to tests, and then scroll down to C, A, B, C, where it says chi-squared test. And it'll ask you, which matrix has your observed counts in it. Now I already have matrix A here, but if it was in some other matrix, if for some reason you decide to go back to that matrix menu and then under names, go to the matrix that you put the observed counts in, but it was already matrix A. And then just make sure that this expected matrix is a different matrix. I know I didn't enter an expected matrix, but it'll do that for me. What you're going to see is that if I have the observed matrix incorrectly, it'll make the expected matrix for me. Alright, now when you hit calculate, the top line there, that chi-squared, that's the test statistic, 10.12. So it already calculates the test statistic for us. And this is more accurate than what you're going to get what they're going to have in most cases, because you see when they calculate the test statistic, they're using these rounded expected values that I'm pointing at, 14.6, 9.3, 15.1, and so on. And when you round values, the more you round, right, the less accurate your final value will get. So there's a test statistic, but what I wanted to show you was it also made a matrix with these expected values. Go back to the matrix menu and you see now matrix B is populated with a 2 by 3. Now you can enter matrix B on your main screen and hit enter and scroll around it and see them. I think the easier way to be to go to edit into matrix B, and there you go. See, 14.6, 9.3, 15.1, then the second row, 15.4, 9.7, 15.9, right, if you were to round all those to one decimal place. Okay, so yeah, very easily done there. Okay, so now, right, now that I've entered all that, gotten that matrix with the expected values as well, then the second part of this question is, what is the test statistic? And they say round the final answer to one decimal place. Alright, now when I looked at the calculator earlier and had that, chi-squared test up, it was like 10.12, right? So 10.1. So you could try entering that. Now it might be a little more accurate than what they want. Alright, you could enter 10.1, and if it says you're wrong, and to try, it'll probably tell you to try again. You're not off by much though. It's going to be 10.1 or maybe 10.0 or 10.2. Right. Now, one thing you could do is, I've got my observed values, and they're going to use these expected values, rounded to one decimal place. So another thing I could do is enter those as lists. Right. Go stat, edit, and then down list, L1. I'll put these observed counts. So again, I'm going 11, 6, 22 for the first row, and then 19, 13, and 9 for the second row. So I enter those observed counts down list L1, and then down list L2, I'll enter these expected values, rounded to one decimal place that they had for me in the last answer. So 14.6, and again, they have to be in the same, corresponding to the same observed value though, right? So the 14.6 has to be next to the 11, and the 9.3 has to be next to the 6, and then 15.1, 15.4, 9.7, and 15.9. Okay, so now I've got all the observed counts, all the expected counts, and then I go up to another empty list, say L3, go up to where L3 is, hit enter, and then I enter a formula where I'm taking those observed, in parentheses, I take the observed counts, which are from L1, minus the expected counts, which are from L2, close parentheses, we're going to square those, and then divided by the expected counts, which were from L2 again. Alright, and then the test statistic will be the sum of all these values, right? The sum of all 6 of these values. So I get out of here, go to the list menu above stat, hit second stat, go over to math, and then you see sum at number 5, and I want to add up the values in list L3. And there's our test statistic, 10. Now you see this came back as 10.17, not 10.12. So this one I would round to 10.2, right? And that's the answer they're going to take. All right, let me show you. See, let me enter 10.1. Now it might take it. It might take it. 10.1 is what I would have gotten if I just ran the chi-squared test. All right, if I just ran the chi-squared test, it came back as 10.12. So I'd have rounded that to 10.1. Oh, okay, it took it. Wonderful. You see how their correct answer though is 10.2. So it looks like there's a bit of tolerance. It looks like they accept a little bit off, because of rounding. Because 10.2, you see, they use the expected values to one decimal place, and again, you would have gotten that 10.17, like I got here, and rounded that to 10.2. But it looks like the calculator version is correct as well, right? If I go stat over to tests, and then alpha C, right, the chi-squared test, and then use that observed matrix and calculate, you see it came back again, 10.12. I would have put in 10.1, and I did that. When I put in 10.1, and it came back, they said, oh, that's good. That's correct. Because it is correct. It is correct. In fact, it's more correct. All right, your calculator thing, if you just enter those observed values into a matrix and run the chi-squared test on your calculator, that value, that test statistic is more accurate than what they're doing. Where they're rounding every single expected value to one decimal place and then calculating it. All right, but it looks like either way is fine. That's great. All right, so hopefully watching me do this, reading the more instruction when you can, when you need to, looking at the answer explanations, reading those, hopefully those make sense to you. I'm hoping all this stuff helps you when you're going about working on this stuff on your own. And thank you very much for watching.